Cool. I think we'll get going. Just one more. Awesome. All right. Thanks everyone for joining us today. I'm here with my colleague Alan to talk about operating a bare metal cloud for Quant Research. We're not here to try and sell you anything, just to kind of show you some of our experiences and kind of the value we've got out of OpenInfra and OpenStack, and how with some hard work and assistance, then you can pretty much do anything with it. So hopefully some of you, if you're on the fence, might choose to go that route. We've been really lucky to have a number of people work with us on this platform for a number of years now. We've been building it for about 7 years, and that includes Stack, as you see, have been with us throughout the whole way. So Aaron and I certainly can't take all the credit. A little bit about me: I'm responsible for all core infrastructure compute provisioning at Research, and that's a mix of OpenStack, VMware, and Kubernetes. I've been there about 7 years. Started in engineering, and now in kind of a management position, and this is my 9th OpenStack Summit.
I'm Aaron Scaife. Been at Research for about 5 years now as an OpenStack engineer, and been using OpenStack since around the Kilo release, one form or another. And that's from small hyper-converged setups to something a bit bigger, as we'll see today.
Cool. So I'm going to introduce Research, give you a bit of an overview of our estate and our stack, and then I'm going to hand over to Aaron to talk about some of the challenges we see at scale. With the kind of quirky constraints that we have. So who are we? We're Research, a quantitative research company based out of London. We take massive amounts of data from kind of all walks of life, and our really clever researchers try to find patterns in that data that can help us predict the future of the markets. They generally figure out, build an algorithm that meets that pattern, and then they'll try and backtest it against data from a few years ago, maybe 3 years ago, maybe last year. And if that all works, perhaps we could pass that research on to our client to look at trading in the markets. We've been doing it for a long time, about 20 years, and that is a long time in core finance. Generally, if you don't get it right, you don't last very long. There's a number of parts of Research. So we have Research Next Gen, and that's really about investing in the future talent. So we sponsor PhD students across the UK. I think we've got 42 sponsorships this year. We do a lot of work with STEM charities, so it's technology, engineering, mathematics, to try and encourage people into that industry and help make it more accessible. And if you're interested in more about that, definitely check the website out for the QR code. And we also have Gross with Jay with us. He has a talk at 4:30 today about the invisible work of OpenStack, and I encourage you all to check that out. Their function for us is kind of like a distributed development team. They're based around the US and Europe, and help GI and all sorts of upstream work. But we're very lucky to have an OpenStack kind of speciality there. The research that we generate is highly valuable, and because of that, there's a really strong focus on security at Research, and that's kind of a foundation of a number of challenges we have, and we'll touch on some of those. So I mentioned we're operating at quite a significant scale. Historically, we've never really talked about this, so when I put this talk in, I wasn't really sure how I was going to frame it, but I was lucky to find this on the website. I'm actually quite surprised to see it there. 13,000 GPUs, 500,000 cores, and up to 50 million batch jobs per day. I'd love for all of that kit to be all the same, but the reality is that is not the case. So it's a really diverse mix of AMD and Intel and all sorts of different generations of hardware, and that presents a massive challenge. It's just a little bit of everything, and as I'm sure you know, that makes things quite difficult. 50 million jobs a day, that works out about 600 per second, which is kind of crazy. And that's a research job that needs to pull down a Kubernetes image, maybe authenticate with Vault, talk to some data APIs, do some processing, and then store a result and ship its logs. Doing that 600 times, just starting jobs per second, is crazy to me. And there's a lot of infrastructure we have to build to support that. So authentication services, databases, metric stores, Victoria metrics, things like that. We call it internally like the Death Star, because pretty much anything you point the farm at melts. So if you're introducing a new service at your research, then you've got to be sure it's ready to scale. And I had to double check this number, 90 billion events and messages per day. That's 1 million per second, which is, again, baffling. So how do we manage all of that? It's the classic OpenInfra blueprint talked about on the keynote. The foundation of Linux, we've got a preference for Ubuntu. We were on Stream, we've moved away from that. We use an awful lot of services. This is just to name a few. Terraform is super key, so all our customers use Terraform to provision on our cloud. We also use it to configure it, so all our network projects, everything's managed with Terraform. We use Vault really heavily. Everything at GR uses service accounts, and so Vault gets a bit of a battering. And we also use it as a sub-CA for PKI, so people can pull certificates from it for their services. We're a massive user of Jenkins. We use that for all of our operational work. We're heavily kind of pipeline orientated, like generally things don't get done manually, it's all through pipelines, and I'll come onto that a bit more in a minute. The classic Prometheus Alert Manager Elk stack for metrics and logs, and as I said, a bit of Victoria metrics as well. The core of the provisioning system is OpenStack. We're running OpenStack Yoga, so we're a little bit behind. We'll work on it. There's 6 production regions that we're operating today, and we have 26 compute and network AZs across those regions. We're in the kind of hundreds of hypervisors, but we're slowly shrinking that a bit as more stuff moves to Kubernetes. And yeah, we're running Yoga, but we're kind of planning what I'm calling the double-double, which is a double slurp. I'm not quite sure how it's going to go yet, so but hopefully we're hoping that'll take us from Yoga through to Caracal. We do operate Ceph in the back end, not so much on the research front, more for like storing images and a bit of Swift and S3, and also for our hypervisor VM storage. We're still running Ceph Pacific, which I'm aware is end of life also, so we're looking at that. And it's all Flash, so quite lucky in that respect. On top of that, we deploy Kubernetes, mostly on bare metal and over 100 clusters. Some of those clusters up to 1,000 machines, so not small clusters, quite significant. I think we're still on Kubernetes 130, and we're moving to Ubuntu 24. And then sort of to top that off, we've got Armada, which is our multi-Kubernetes cluster batch scheduler. So for our research, that's one endpoint that they can hit, push their jobs, and they can get distributed across any of those Kubernetes clusters, and they don't need to understand the details of that. And that takes care of all the scheduling. So a couple of years ago, and kind of the preface for this talk is that a colleague of mine, Scott Solkin, did a talk in Vancouver about our architecture and what we built for building this. And he did an amazing job of explaining that, so I'm not going to rehash it. His talk was called Deploying and Managing Bare Metal Kubernetes with Ironic, so it's on YouTube, do look it up, it's worth a watch. What I find kind of amazing is even though he presented that 2 years ago, we were designing it 2 years before that, we're still deploying that method today, and it's still scaling well, so it stood the test of time, which is great. He covered a lot, but he didn't cover some of the challenges that we have day to day, so I'm going to cover some of those. So firstly, speed and scale. So our researchers demand the absolute best from us and their latest hardware, so everything needs to be bigger and faster, more performant, more memory, and that presents some challenges. Sometimes we're having to deploy hardware that's not been used by a lot of people. That causes us an awful lot of headaches, and usually in the firmware realm. I think Aaron touched on that a little bit. And everything you do suddenly becomes really hard. Like just building a Kubernetes node, you need to, you boot your IPA, you pull an image from Glance or from wherever, and you build a node. And maybe that's a 5 gig image, but if you're building 100 or 1,000, suddenly it's 5 terabytes of data, and you need to start thinking about, do you have enough Glance patch? Do you have enough conductors? And are their caches completely appropriate? And that's just one small thing, there's like 1,000 of those. We operate something we call like a high integrity mindset. I'm not sure how many people operate like this, so do come and tell me then if you do. And the idea is that no single person can modify something in production. or even access something in production. So everything needs two pairs of eyes, four eyes, and that is from absolute beginning. So like source code to running in production. So everything is pipelined, everything is locked down, everything is branch protection, everything from source code through Jenkins and how it builds images, how they're stored, and then how they're rolled out to production. We also heavily RBAC our users, so including ourselves, our administrators. So we have a really minimal set of permissions, only things we need to do day to day. And the idea is that if you have issues, the troubleshooting should be done via pipelines. So as an example, if we have a Ceph issue, maybe Ceph goes to error, something flashes up on a dashboard to say Ceph's not having a great time, we would run a pipeline that would run a whole bunch of debugging stuff for us before we kind of make the leap and jump into the system. And it's just all about protecting that core IP that runs it. If we do need to SSH for a production machine, we can do that, but it's again, there's a process and there's an audit and a review. So we try not to do that when we can. We heavily rely on encryption, so everything from BMC of the hardware box to our RAID controllers, and we use remote key management for those. We do encryption on both sides of the operating system, and kind of like so everything from live migration, databases, all of our APIs, obviously internal and external. Everything's encrypted. The only thing we kind of haven't looked at is like secure enclaves and confidential computing, so I think that might come in the future. And we also implement rolling rebuilds. Does anyone do that? No? Okay, I'll just explain that. So the idea there is that we aim, or aspirationally, we rebuild all our systems every 30 to 90 days. And that is from scratch. So tear the whole machine down and rebuild it. And actually are the people that are doing that the best are the Kubernetes teams. And that causes an awful lot of churn on our clusters, which again now we'll talk about some of the numbers. And then to add to all that, we're also completely air gapped. So actually getting code in is quite a challenge. It has to go through a number of proxies and scanners, and we can't just move things in and out as easily as some people might be able to. We don't have just MacBooks that can use the internet, we have to use special laptops and things like that. And we need to manage all of that whilst providing a world-class user experience to our teams that do research. Generally they all strive to be the best at what they do. We try to do the same. And as such, we have like a minimal appetite for outages. So we've never kind of done the side grade tactic or anything like that. We've come all the way from, I think, Queens to Yoga, just upgrading the same environments and growing them. And also moving completely from CentOS to Ubuntu, again, without any new clouds or anything like that. It's all in place. We kind of have almost like a no expense spared control plane. So some big dedicated servers for running all our APIs and databases. And the reason for this is when Terraform starts managing thousands of resources, like Kubernetes nodes, the resources multiply, and even to just run a plan, we get, I don't know how many, 20, 30, 50,000 API calls. And we need to be able to service that as quickly as possible. And we track and advertise our platform SLI, so we make a point about the reliability of our service, and we get our users to kind of keep pushing us to provide a better service. So that's just a quick overview, and if anyone wants to talk to me about any of that after, feel free, and I'll hand over to Aaron to talk a bit about how we're doing this at scale.
Cool, thanks. So a very quick overview of what we're doing to sort of roll out Ironic and OpenStack. Fairly standard recipe, built with Collar and deployed via Collar Ansible. We try and minimise any sort of custom code that we need in the OpenStack services. Occasionally we have to fork something, perhaps for performance or stability reason, or perhaps some business logic inside GR. Most of the stuff that we can push upstream, we do so often with the help of the open source team. As we sort of mentioned before, there's some sort of design specific considerations, things like conductor groups, and everything we deploy is deployed via Jenkins, and all of our configuration is stored as code. Things like images and network subnets are all laid on top using Terraform. So, as I said, fairly standard recipe, and it enables us to scale our control plane or our region to these in minutes or hours. So with that said, what do you need to tune Ironic and OpenStack for thousands of nodes? I think when you've got a handful of nodes, things generally work hands off. When you start getting into hundreds or even thousands of nodes, any sort of small inefficiencies or downstream dependencies you rely on can quickly be melted. So things like your database or your package mirrors, anything like that. But the good news is Ironic and OpenStack does a great job of hiding any sort of failures. So things like port binding issues, usually really tried, and does a good job of smoothing that sort of thing out. But what we found is that things like when you're running network generic switch to change your access VLANs as a server's provisioned, you can quickly melt your TACAC server or even lock up a whole switch with concurrent SSH sessions. So how have we minimised some of these issues? Well, the standard stuff like increasing the API worker counts. For Ironic Conductor, the big one for us was the power state sync interval, so how often Ironic Conductor will actually poll the VMC. When you've got a large number of nodes, that can very quickly cause issues. Concurrent build throttling, so Nova Compute Ironic offers the feature to limit your concurrent builds. So for us, I think that we've got that set to around 50 per conductor group at the moment. We have had higher number of concurrent builds in the past, but we kind of favour reducing that a little bit for stability reasons. And the really big thing for us is gathering data on this stuff, so metrics. So we're using the OpenStack exporter, the bare metal data that comes out of that. And something we've enabled is Oslo messaging notifications, which gives you a really rich source of data, which we feed that into Elk, and then we analyse that data and present it up on Grafana, which I'll show some of that in a minute. So this all gives us sort of insights into the stack, and it also gives us insights into some of the things that sort of plastered over by Ironic, so those port binding errors, port binding errors and things like that, that to a user might be invisible, but actually at the platform layer, there are things that are being retried, and we can focus our efforts on investigating those things. And just one example actually, so a researcher built a new Docker image which contained a new package. That package calls the AWS metadata service, which is the same URL as the OpenStack metadata service. And once that was deployed as a massive job on the farm, we had several thousand requests a second to our metadata service, which was hammering that MLDB. But because we had the metrics and data to sort of identify the sources on that, we were quickly able to sort of contain that. So, keeping things resilient, I mean, it wouldn't be kind of an OpenStack talk without a call out to RabbitMQ. We recently migrated to Quorum queues. There's quite a lot of resources out there that discuss that, so I'll just touch on it very briefly. We've sort of gone through several iterations over the years, from classic, mirrored, and even considered a single node at some points, semi-seriously. But we've settled on Quorum queues, and that does seem to be more stable, particularly when you take a node out of servers. But the big thing to consider in sort of the Ironic realm is Nova Compute Ironic. There's not a stable HA story for that at the moment, as sort of mentioned in the docs. So it needs careful consideration. So for us, using Collar Ansible, we can migrate the Nova Compute Ironic service between hosts. And actually, just to mention, for those not familiar, a Nova Compute Ironic service is used to present Ironic to Nova as a hypervisor. So it means that users can effectively provision a bare metal server using the same APIs that they would a VM. But as I mentioned, there's issues with this in that if your server that's hosting Nova Compute Ironic dies, you migrate it to a new host, but your original copy comes up, or your initial service comes back up, you can end up with race conditions and other problems. So you need to kind of think about your operating sort of like runbooks, or how you deal with that if that was to happen. And both of these two topics here that I've mentioned kind of ties into what Ross was talking about, which is automated rebuilds. So our aim is to completely rebuild our OpenStack control plane every X days, and by leveraging both of these and the automation in Ansible to actually migrate an open computer Ironic, we can go a long way to doing that. So we mentioned our researchers often want the latest hardware, and that's great, but there's a lot of problems with that, or can be. So things like BMC inconsistencies, if you're running OpenBMC, for example, vendors can often layer their own sort of sprinkling of OEM-specific quirks on there, should we say. And the latest hardware is often very prone to firmware issues and bugs. So one we've seen recently is applying a CA cert to the BMC. Actually stopped the entire BMC from communicating with the BIOS internally. So to set the node to Pixie boot, or even turn on or off, stopped working. So in that case, you might have things like your enrollment scripts outside of Ironic or things like that might need to be updated to deal with this new hardware. But the good news is that Ironic provides multi-arch support now, so we're running a lot of ARM kit and x86. The drawback to that is actually sometimes the vendor support isn't always there, or packages aren't always there for ARM, so you can end up with compiling things or stuff like that. So we spent a lot of time building hardware validation. So there's some features upstream in Ironic, so things like burning, GPU, CPU, memory burning, disk burning, all of that. We've built custom checks for Ethernet and InfiniBand cabling. So deploying large numbers of nodes in the data center, invariably there'll be cabling issues from time to time. So we've got detections for whether or not a node has its cables plugged in backwards using LLDP data, and we've got some checks from InfiniBand, making sure that things are in a rail optimized fashion, and some other checks up there. And when we enroll a node, we will actually go through a full process of deploying a test instance on there, so we can make sure that the node is in a good state before we hand it over to users. And as part of that, we'll also perform burn-in tests. And with the Ironic RAM disk, there's often more packages that need to be installed, in our case, for when we're doing sort of more of the custom stuff. That can actually lead to a RAM disk which is bloated out. Some nodes will fail to Pixie boot if the RAM disk is over a certain size. In some cases, 1 and a bit gigabytes. So one tactic we've employed to get around that is to use standard compression, which rather than gzip with disk image builder, and that shrunk it quite a bit. Some systems take 30 minutes to post. There's no escaping that. But things like doing a RAM disk boot, so your nodes are effectively ephemeral, can go some way to removing a reboot out of the cycle. So, how do we deal with sort of failed hardware at scale? So, as mentioned, the hardware can be quite, from time to time, unreliable, especially the newer stuff. Newer firmware versions go some way to solve that. But you've also got the other problem of older, aging hardware, which is more susceptible to failures as well. So, what we've done to deal with that is to build something called Ironic Self-Healing, which is a collection of Ansible playbooks and roles, which is driven by Jenkins. And what we do is we've encoded like some logic and heuristics to detect the most common failure modes. So we'll query the BMC, check if there's any failed hardware, or if a node goes into maintenance or clean failed state, we'll run Ironic Self-Healing against it, try and get it back into a state where it can go back into the pool. If that's not possible, then we will raise a ticket for the DC team to have a look at. So if we detect, for example, failed disk in the BMC, we will then raise a ticket, set the node to maintenance, and once the workload's drained off of there, the ticket will be acted upon and new disk put in, node gets cleaned and back into the pod. So this is an example of some of our metrics, which is driven from the Oslo messaging notification data. And what this shows is a node which has had, if you look at the top two rows there, we can see it's active and available. So this is a node which has had, over the course of maybe a day, quite a high number of instances on there. So that may signify that there's a problem with this node, which warrants investigation, or it may simply just show that the user's testing something and rebuilding it 10, 15 times in a day for some reason. But what this allows us to do, though, looking at the bottom, is we can track which instance has been on which node and present this to an operator in a nice way, without them having to go over logs and sort of cross-reference it themselves. And you can see here, this is some of the build stats that we've got. The colours on the left-hand side simply relate to regions. So at sort of the busiest times, we're doing about up to 3,000 deployments per day in Ironic. And you can see we've got failures on the right-hand side there. And as I mentioned earlier, around TACACs falling over all your switches. Sometimes we're doing up to 15,000 logins a day on the switches. So if the user were to rebuild a whole rack of servers at once, network generic switch is going to SSH those switches a whole bunch of times during that deployment flow. And more data that we're pulling from via the Oslo metrics. We can see here there's how long it takes an average build, for example. And so I guess putting it all together, what do we end up with? Well, we've got a bare metal cloud which supports multi-generations of hardware, multiple architectures, and we're doing sort of 33,000 rebuilds in a month, and pretty successfully, just under 99% success rate, but that's still not as high as we'd like. So Ironic's doing all the heavy lifting here. It's abstracting and masking the failures, and that's really doing the hard work here. But for us, we can assign a dollar value for every core and GPU that's not available at any one time. So shaving a minute or two off provisioning time can actually lead to quite a big, dollar value for us. So very quickly, our future plans. So we're going to have a big drive on standardization. Redfish driver, virtual media is the big one for us. So removing the entire Pixie boot flow. And we think that will go some way to actually improving our build reliability. We no longer need layer 2 there, so we can rely on just layer 3 for all of our provisioning. And Ironic runbooks, so giving people the ability to self-service nodes, so we can put things like firmware updates into the hands of users or some other predefined service flows. And remote console, which is a feature which landed recently. For us, we'll likely implement that as a read-only we'll deploy it in a read-only fashion to begin with, possibly using serial console, but the graphical feature is there too. And call out for trait-based port scheduling. So if you've got a node with multiple NICs on it, you can deploy, you can sort of set metadata on networks, and then Ironic will do the mapping of that network to different ports, and it could let you assemble sort of multiple, more dynamic bonding, so 4 ports rather than 2, for example.
That should land upstream in Gazpacho, so that is in progress, and y'all get it upstream in 2026.1.
Cool. So look out for that in 2026.1. And then container-based steps in the IPA, so moving Docker containers into the IPA to run certain things like firmware updates. Cool. And I think sort of finally, I guess in summary, hardware has its quirks, but Ironic gives you a great framework to provision complex hardware at scale. Some of the complexity I've spoken about there is sort of GR specific, I guess. So thanks to the upstream, HPC and our sourcing as well, and we're hiring in London, so find us if you may be interested.
Thanks.
That's the first time I've seen that success rate number. You know the conversation we had on the other day where I told you I gave a whole bunch of advice about how to measure things, but I didn't know if they had done it or not? It was done. That was the number I was trying to give them to push over everything else. So that is impressive, especially for a mark global life. So that is,
No.